Section 7.5, the central limit theorem. In the last section, we talked about sampling distributions for sampling means, and the second criteria that was required for us to make a sampling distribution was that we needed to either have a population that was normally distributed or a sample size that's greater than or equal to 30. Here's a little more detail on why we need that. Let's say we have a distribution that's uniformly distributed like we have here. If we randomly select just two values from this and average them together, we can see that we're most likely to get a value right in the middle there, right in the middle of our distribution. If we pick a value from this side, okay, it ends up being counterbalanced by one on the other side more often than not. The bigger our sample size gets, the more consistent we're going to get. So our averages get closer and closer to that true population value, and it's harder and harder to get results, averages, that are far away from that. And that goes for any distribution. So we see here we have a distribution that's skewed to the right. If we take a sample of size 2, it's still skewed to the right, but a little less so. If we take a sample of 25, we can see those values are piling up around that true mean, and it's not likely for us to be too far away from that. One last example, let's say it looked like something crazy like that, where it's just like a valley. This is what our distribution looks like if we take a sample size of 2 and a sample size of 25. So for the sampling distributions of sample means, if we have a sample that's 30 or more, we can assume that regardless of what it looks like to start, our sampling distribution of that size is going to be approximately normal. This is called the central limit theorem. As our sample size increases, the sampling distribution of X bar changes shape. It looks less like the population distribution and more like a normal distribution. The bigger the sample size, the more normal it gets. The mean is going to be the same in all of these, although we'll see it more as the sample size gets bigger. We see those observations pile up around the true mean. And that standard deviation is that same standard deviation that we talked about in the last section. Central limit theorem, we'll just abbreviate with CLT, all right? And it's the fact that we end up with a normal distribution once we're talking about taking a sample of 30 or more. So recall that when we take a sample, the mean of our distribution is just going to be the mean of our sample. The thing that will change is the standard deviation. And that's what's determining whether or not this is approximately normal. So our sampling distribution will be approximately normal when either of the following is true. So to start, if the population distribution is approximately normal, we're going to have an approximately normal sampling distribution regardless of what the sample size is. So we could have a sample that's really small, say 2 values. We will still get something that's unimodal and bell-shaped. If we don't know what the population shape is, or if we know it's not normal, we're going to have a sampling distribution that's approximately normal as long as n is greater than or equal to 30. The more skewed it is, the farther from normal it is, the bigger this has to be, but generally speaking, this is big enough to always result in a approximately normal sampling distribution. If one of these two criteria isn't met, our sampling distribution is going to have some characteristic of the population, like on that previous slide where we started out with something that was skewed to the right, and our sampling distribution was still skewed to the right, but just a little less so. Mr. Ramirez's class did the penny for your thoughts activity from the beginning of this chapter. The histogram shows the distribution of year for the 2,341 pennies in his collection. So this is the whole population of all the pennies that they could sample from. Let's say we were to take a sample of size 2. What would the shape of that population be? All right, and how would that compare to a sample of size 50? Since this distribution is not normal to begin with, it's very heavily skewed to the left, we need a sample that's greater than or equal to 30 in order to have a sampling distribution that's approximately normal. This one is not, which means it's going to retain the characteristics of this distribution. So the sampling distribution of size 2 is still going to be skewed to the left, although it'll be a little less skewed to the left. For a sample size of 50, because that's greater than 30, our sampling distribution of means will be approximately normal by the central limit theorem. And here's the actual data from samples collected from Mr. Ramirez's class. We can see when we have a sample of size 2, this is still skewed to the left, but less so than that original population. And when we have a sample of size 50, thanks to the central limit theorem, because that is greater than 30, we can see this is approaching that unimodal and bell-shaped distribution. Also, just a note, if we look at the ranges here, the range on this graph is about 50 years, where the range on this second graph with a sample size of 50 is only 8 years. Okay, and that's because as our sample size increases, the standard deviation decreases. There's less variability in larger samples. So when we take 50 pennies and we average their years, we start to get really consistently values around that true mean of all the pennies in the population. It's unlikely to get something farther away from that we see in this graph. When we take small values, small sample size, we can still kind of see where that mean is, right? But we're not getting things that are nearly as close as we do when we have that larger sample size. Let's suppose that the number of texts sent during a typical day by the population of students at a large high school follows a right-skewed distribution with a mean of 45 and a standard deviation of 35. X bar is going to represent the sample mean for the number of texts sent by a sample of 100 students. That's our sample size. What would this distribution look like? Well, the shape will be approximately normal because this is greater than 30. Okay, so does it matter that it's skewed right to begin with? Because this sample size is greater than or equal to 30, we're going to get something that's approximately normal. The center will center around that true mean of 45. And the standard deviation is going to be calculated with this equation down here. So sigma, the population standard deviation is 35. We're going to divide that by the square root of the sample size, and we get 3.5 for a standard deviation. Now, using that information, how likely is it that a random sample of 100 students from this school will average at least 50 texts per day? We're going to go ahead and draw our normal curve with 45 right in the center and a standard deviation of 3.5 texts. And then we can go ahead and calculate a z-score for 50. So our z-score is 1.43. We looked that up in the table. Remember, the table is going to give us the value to the left there. So we need to do 1 minus to get our answer, 0.0764.